Hello, my name is Alberto Sonnino from UCL, and I'm going to present you a paper called Replay Attacks and Defenses Against Cross-Shard Consensus in Sharded Distributed Ledgers. This is joint work with my colleague from UCL, Bano, Mustafa, and George. So here is the initial setting. We have a set of nodes, the green one are good nodes, and some bad nodes, the red one, which are Byzantine and may act arbitrarily. Whatever happens, we have more than 2/3 nodes which are honest. What we want is to allow a client to submit a transaction to the system, and the system would order those transactions despite the presence of the bad nodes. We focus particularly on state sharding. So state sharding would work as well. Instead of having all the shards running consensus with all nodes running consensus with all other nodes, we separate the nodes into subsets called shards. Then each shard will run the consensus algorithm within the nodes of its own shards and would run a cross-shard consensus algorithm to communicate and coordinate with other shards. So here is an example transaction. We have x1 and x2, which are the two inputs that live respectively on shard 1 and on shard 2, and 3 outputs. Once this transaction is executed successfully, all the inputs are deleted and all the outputs are created. There are only 2 possible outcomes that are successful for such a transaction. Either the transaction is aborted, that's on the left, where we have all the inputs that are there and no output objects that are created, or if the transaction is a success, then all output objects are created and all inputs do not exist anymore, they're consumed. Anything else would be a failure and a safety violation. Cross-shard consensus is the arrows that you see there on the right, is how those shards communicate with each other. And we study here 2 papers, S-BAC from Chainspace and Atomix from Omniledger. Both present a very similar solution, but I'm going to illustrate the one of Chainspace. So S-BAC works as follows. We have a transaction key, which the client submits to all the input shards, so all the shards that handle at least one of the input objects. So shard 1 and shard 2. Those white boxes labeled BFT are actually all the nodes of the shard that would run a BFT consensus among themselves. Those can be PBFT, hot stuff, or any kind of consensus algorithm. Then the transaction, each shard needs to decide whether the transaction is valid or if it needs to be aborted. So if the transaction is valid, the shard would lock the object x1 and x2, so no successive transaction can try to consume them, and would emit a pre-accept message to the other shards to signal that they're ready to go ahead and commit the transaction. If the shard here all pre-accepts message from all input shards, it deletes the input object that it handles and creates the output object. Then it signals that the transaction is to be accepted to the client, and it sends a message, the same message to shard 3, which will create the output object. Atomix from Omniledger works in a very similar way, but reflects all the messages through the client rather than broadcasting them across shards. So those 2 protocols work fine, but it seems that they're insecure under parallel composition in their current implementation. And here we show some of the attacks that can happen against those systems. So an attacker can double-spend any object, and it does not need to collude with any nodes. It can act as a client or as a passive observer. And for some attacks, as the one that I'm going to illustrate now, it can reorder the network messages. So here is an example transaction T, which has 2 input objects. Let's say that there are coins, one coins 10 and one holding 5 coin, and creates the output object of equal amounts. So now the attacker first creates a fake transaction, T prime, which is doomed to fail. It contains x1 tilde as input, which is an object that does not exist on shard 1. So first step, the attacker sends T prime to shard 1 and shard 2. So it submits that transaction. Of course, shard 2 thinks that it's all okay, x2 exists, so it will lock the objects and prepare to send a pre-accept message to shard 1. But shard 1 will realize that x1 tilde does not exist and then broadcast a pre-abort. However, now the adversary uses this ability to reorder the network messages. and quickly stops the protocol and sends transaction T. So shard 1 will receive T, seeing that X1 exists, and will send the pre-accept message. However, shard 2 will see that X2 does not exist anymore, or at least it does exist, but it's locked because of transaction T prime, and therefore will send pre-abort. As a result, transaction T is aborted. However, over this whole process, the attacker managed to record a pre-accept T message emitted by shard 1 that you will later use for a replay attack. Then the transaction T prime can continue, X2 will be unlocked by shard 2, and the transaction finally aborts. Next step of the attack is the client that submits a transaction T star, which moves the coins X1 through another of its own account. So it consumes X1 and creates Y star instead. It doesn't matter in which shard it lives. Now, the final step of the attack, the client resubmits again transaction T. This time, shard 1 will send pre-abort because X1 has just been consumed by T star. And shard 2 would send pre-accept and lock the object X2 because X2 still exists. However, now the attacker erases shard 1 by sending the pre-recorded pre-accept message from before to shard 2. Then shard 2 is fooled into believing that shard 1 sent a pre-accept message, and since itself sends a pre-accept message, it sends accept to shard 3, which creates the output object Y3. And then shard 1 may still send abort, but that doesn't matter much. So here is the outcome. Before, the attack had 15 coins, X1 and X2. And now, as a result, it has 24 coins, Y star, Y2, and Y3. So this is one of the possible attacks that can happen. And we propose a solution called Byzcuit, which is a mix of S-BAC and Atomix, and hopefully present the best of both worlds and is secure under those attacks. So I don't have time to explain it how it works, but the full details are on the paper.